Hi guys, welcome back to our pre-lecture videos. Today we're going to be talking about relative velocity and relative motion. So let's jump right in. What is it? Why is it important? Well, basically relative motion is our concept of the comparisons we can make between two objects as relative accelerations and velocities. So just like all of our previous units and videos, this is going to be all about vectors. So you'll see here a list of examples of how relative motion you might see it in the real world. We're going to be focusing on these two right here, a boat on a flowing river relative to a bank, and then two cars in motion. So we're going to start with this last one right here. Let's say, for example, you and a friend are driving on a highway. You could be going 60, they could be going 65, or any other value. And if you have this guy on the side of the road watching you two go by, well, he's going to see you guys going at these values. But if you're in your car and you look over at your friends, well, what are you going to see? You're going to see something different. You're not going to see those 60, 65 values. And how do we describe this difference? Well, we use something called a frame of reference. You, your friends, and the person on the side of the road are all making your measurements from your own frame of reference. And all a frame of reference is a coordinate system in which you're making these measurements. So it's also important to note that two different frames of reference may be in motion relative to each other, just like we saw. So we've got our example here. Maybe you have your frame of reference on the page. Then you got your little snail friend. He just rolled right on by. He's got his own frame of reference, right? They're interacting together, but you're going to see different things. You're going to see that snail's motion a little differently. So let's do another example. We've got an animation here. You're on a boat, right? This boat is going out to sea. Its motor is going to push it straight this way. That's the direction it's going. That's going to be a vector velocity of the boat with respect to the ground, which you'll see in green here. But there's also going to be another velocity acting, which is that of the water. The water is moving on its own with respect to the ground, and that's this red velocity here. So to actually get the true motion of this boat, you're going to have to do some vector addition, and you're going to do a vector triangle here, and you're going to get this velocity of the boat with respect to the water in blue going out in this diagonal direction. All right, so maybe this might be an easy example to understand, a little bird's eye view. Normally without a current, you're going from point A to point B, straight across horizontally. But if you have a current, in this case, your river is going up in this direction, it's going to push you this way, and you're going to get this nice little triangle vector. Okay. All right, so let's look at a more concrete example. You'll see that every person in this cartoon here is going to be seeing the other people move in different ways. And note that person B here cannot see person C directly. So if person B wanted to know C's velocity, how would she go about doing that? Well, we have a mathematical way, and we want you guys to note the style of notation here. So you're going to have your velocity v, and then you're going to have these subscripts here that denote the whose velocity you are calculating, and then from whose point of view it is, right? So VCB is the velocity C relative to B, CA, the velocity of C relative to A, etc. So we have our problem. If person B wants to know the velocity of person C in regards to her, she could ask the man pulling her, person A, to tell her how he thought person C was moving, and he would respond with a value V sub CA. So from his point of view, looking at him, correct? And then she could also note her velocity relative to person A and get this value V sub AB. And then as a combination of the above two, she could express the velocity person C with regards to herself, person B, right here. So let's look at another example, maybe a little bit easier to understand. It's in one dimension. You've got somebody moving on a train here. So the velocity of the person with respect to the train, 2 meters per second. And then you also have the train moving, the velocity of the train with respect to the ground at 9 meters per second. If you have an observer here watching this person, he's going to see the person moving with respect to the ground, right? So put these two together just like before, and we're going to get this value, VPG, which is 11 meters per second. Just one more example, a more 3D one. Let's say you have a passenger on a moving cart. They're moving in this direction diagonally, our velocity PC this car's also moving on the rails at a velocity cg. How are you going to find the velocity of the passenger relative to the ground? Well, just like before, we'll do our vector triangles, we'll do tip to tail addition, and we'll get this final vector, our vector PG. All right, guys, thank you guys for listening, and I'll see you next time.